Hello, I'm Namiko Saito from the University of Edinburgh. I will present a work on latent object characteristics recognition with visual to haptic audio cross-modal transfer learning. Recognizing the characteristics of objects while a robot handles them is crucial for adjusting motions that ensure stable and efficient interactions with containers. Otherwise, the containers would be mixed, toppled, and damaged. Ahead of realizing stable and efficient robot motions for handling and transferring the containers, this work aims to recognize the latent and observable object characteristics. We selected shape, position, and orientation as the object characteristics. In previous research, they realized detecting characteristics with tactile, sound, and vision. However, they have not realized recognizing unobservable latent object characteristics dynamically as the robots perform tasks. Therefore, we propose a two-phase learning framework to realize latent object characteristics recognition. We initially train the model with vision directly observing the target objects, and then we transfer the latent space learned from vision to a second module, trained only with haptic audio and motor data. This transfer learning framework facilitates the representation of object characteristics using indirect sensor data, thereby improving recognition accuracy. This is the learning model. The first phase vision module aims to predict object characteristics from RGB images in situations where objects are directly observable within the container. We use a fully connected layer from the latent space of the VAE to output continuous values representing position and orientation, and shape labels. The objective of the second phase learning is to predict object characteristics using time series data from haptic audio and motor data, useful for when direct observation of objects is unavailable. The structure of this module comprises an encoder part of VAE and a long short-term memory with a fully connected layer. After training the first phase module, we transfer the latent space value, highlighted in red, to the second module to use it as the initial value. The latent space should encapsulate the information necessary to predict object characteristics. For collecting training data, we control the robot to move randomly and recorded image, tactile sensors, microphone, and force torque sensor data. From this slide, I will show you the result. We applied principal component analysis on latent space after training the first phase vision module, which is transferred to the second phase haptic audio module. Observing the PC3 and 4 space, object shapes are ordered according to the size of the objects, and on PC1 and 6, the representation of orientation demonstrates degrees in a circular manner, and PC4 and 5 expresses the X and Y positions in the box. In conclusion, the latent space effectively distributes and represents geometric and spatial information of the objects, which can potentially provide variable support for the second phase learning. For test, we only use indirect sensor data without image to detect object shape, position, and orientation while the robot moves the box randomly. The arrows show the prediction result. We don't use the image for the prediction, but for easy understanding, we are showing the ground truth by image with the red rectangles. We also confirmed with 8 untrained objects. Despite their characteristics differing from the trained ones, the proposed model demonstrated the ability to recognize the latent characteristics. Here, the left figures show the prediction error of position and orientation. Although these errors of our model are larger when compared with using vision for prediction, that is a much simpler problem setting because the position and orientation are directly observable in that case. Our model shows much smaller error than the baseline, therefore this indicates that our proposal contributes to the accuracy of predicting position and orientation when only using indirect observations. The tables on the right display the results of shape recognition. As a result, our proposal exhibited the highest accuracy in shape recognition. Thus, this suggests that the second module could leverage the first phase and further improve shape recognition. Here is a summary, and thank you very much for watching.